Hello everyone, welcome to the week 6 interaction session for the course on control systems. My name is Soumya and I'm a PhD student at IIT Gandhinagar. So last time we had read something about steady state errors, some type of system and basically Routh-Howes criteria. This time we are going to proceed with steady state error part basically, and then we'll go like if you're giving various type of inputs, what is the behavior or the steady state error that is shown by the output of the system. And later on we'll have some basic introductory questions to the root locus, and once we are done with that we'll have some more questions on root locus in the next class. So as of now, we'll start with the steady state error. So what happens here is, you see closed loop transfer function you already know is given by ys upon rs is equal to gs upon 1 plus gshs. It is well known for negative feedback system. Now let us assume that the closed loop is stable, and then if we try to find out what is the ratio in between steady state error to the reference input, then we get es upon rs to be equal to 1 plus gshs. How do we get this? We had seen in the last class also that this ys can be written as rs into gs, right? And what is gs? This is equivalent to rs into cs into ps, right? Okay, so that is called gs. So let's ignore this and let's say if we write only rs is ys is equal to rs into gs, you cancel out gs terms on both the side and you end up with this equation. So es is equal to rs upon 1 plus gshs, right? Where gs is the forward path transfer function, hs is the feedback path transfer function, gshs is open loop transfer function. All right, these are the names that you're supposed to remember. Then when you try to find out what is steady state error, so it is basically limit t tends to infinity and what is the error going to be. Okay, so we want to know the error only when the system reaches a steady state or the output reaches the steady state. So if you apply final value theorem, what do you get? Limit s tends to 0, s of es. This we have done multiple times because if we don't wish to go into time domain because the calculations can be cumbersome. So in those cases, we might like to solve everything in Laplace domain only and find what is the steady state output or error, any sort of thing. So s into es can be written in this way, right? It is very simple. So gs can, let's say we have gs to be some polynomial as numerator and some polynomial as denominator. Now what we want to get rid of any s term. If we are able to take out any s term as common and separate it, so that would identify what is the type of system. So you can see here for this numerator, you cannot take out any s, or if you were able to take out, then also you would have some s in the outside. Here also you are supposed to take out any s that is present over there. Once you have every common s to be out, then you can write s to the power n. Okay, so whatever s is coming out, you have something as power. This n determines the type of the system. So if this n is 0, it is type 0 system. If this n is 1, this is type 1 system. If this n is 2, this is type 2 system. All right, so this is how you define what is the type of the system. So this is the way in which it goes, and we'll have some problems on this also, so we'll see them. So taking you through the notes itself, we can see very well that we already read this formula. S limit s tends to 0, SRS upon 1 plus GSHS is the steady state error. Now, if a unit step reference input is given to the system, what would be the steady state error? So if we wish to know that, so RT here is 1, that means RS is equal to 1 by S, right? So here ES is equal to limit SRS upon 1 plus GSHS. Now here we get 1. Why have we got 1 here? Because RS is 1 by S and S was already there. Both of them cancelled out and you got 1 here. Alright. Then what you can write? 1 upon 1 plus G0 S0 when you try to put S is equal to 0. So this term, this whole term is called Kp. So Kp is limit S tends to 0 GS HS. Alright. So this is the way you write this. Now, so you've got, if it were a type 1 system, this would have been the solution, right? Why this would have been the solution? So see, what you wrote, limit s tends to 0. You know that these terms are already cancelling out, and you have 1 plus gs into hs, all right? And you try to find for this. Now let's focus on this kp term only, because this would be same for each and every, this would differ for each and every case. So your kp is limit s tends to 0 gs hs. Now, how would this kp behave in all the cases? So if it is a type 1 system, type 1 system means what? There is no s in the denominator. So it is some polynomial upon some polynomial with no s in the denominator. If it does not have any s in the denominator, then you would put s, the value of s here, you will put the value of s to be 0 here, and you would end up having some number which would be k. So that is why it is written kp is k, and steady state error is, you saw from here that it is 1 upon 1 plus k, right? But if you go for type 2 system, what would happen? kpe is equal to limit s tends to 0 gs hs, right? So what would happen here? Limit s tends to 0. Here you would have some quantity upon some quantity and s here. If you have s here, you put s is equal to 0, right? If you put, and this is the value of kp, you put s is equal to 0, you will get infinite. So this is why this is infinite. And 1 plus 1 upon 1 plus kp would give you, this would be infinite, right? So everything would be 0. So what you get here is this quantity. Similar argument goes for this also. All right. Similarly, if you have steady state error to unit ramp input for all the types of system, you can see that you will get this thing. This column would give. So anything, you'll have infinite steady state error for type 0 system, whereas you will have some finite value for type 1 system, and for type 2 system, you'll have 0. Similarly, for parabolic input, you'll have all such things. So in the end, this is taken from Ogata book, which is modern control engineering. So they have written in this type of table, steady state error for type 0, type 1 and type 2 system. So I believe that you should remember this table. If not, you will be able to derive definitely, but still it is of much help when it comes to this formula. It is really handy. Okay. So we'll start with some questions here. So consider a second order plant governed by y double dot t plus 4y dot t plus 3yt is equal to ut. All right. It is desired to design a unity negative feedback closed loop control system, okay, with using a proportional controller. Then closed loop stability would be achieved for, so you see it might use something like Routh-Hurwitz criteria, but since it is just a second order plant, we'll be able to figure out just by seeing if all the coefficients have the same sign or not. So that is really a sufficient, necessary and sufficient condition for second order system. So we can try to derive the transfer function. So if you convert this differential equation into Laplace domain, you'll get s square ys plus 4s plus 3ys is equal to us. Then ys upon us would be 1 upon s square plus 4s plus 3. All right, you can write this it as s plus 1 into s plus 3 also. So this is basically your plant transfer function ps, because this is ys upon us only. Okay, what does the question demand? That your cs should be kp. So what is your gs? gs is cs into ps. So it is kp upon s plus 1 into s plus 3. Okay, this is your gs, and it is given that it is unity negative feedback. So hs is already 1 here. If hs is 1 here, then we try to find what is closed loop transfer function. and then we try to stabilize the system, right? We need to have the characteristic equation of the system to do that. So closed loop transfer function can be written as Gs upon 1 plus Gs Hs. What is Gs? Kp upon S plus 1, S plus 3 upon 1 plus Kp upon S plus 1, S plus 3 is equal to Kp upon S plus 1, S plus 3 plus Kp. Okay. So you can again break it in that form only. Kp S square plus 4s plus 3 plus Kp, right? Once you get this, what can you see? Since it, so what is the characteristic equation here? S square plus 4s plus 3 plus Kp is equal to 0. This is your characteristic equation. Once you have the characteristic equation, to make sure that no poles lie in the right of the S-plane, what is the criteria? The polynomial should be a Hurwitz polynomial. What is a Hurwitz polynomial? All the coefficients, first of all, there should not be any for let's say any power of s. The coefficient of any power of s should not be 0. If it is second order, it should have the coefficient for s square, s to the power 1 and s to the power 0, which is already satisfied in our case. Second criteria is all the coefficients should have the same sign. So since the coefficient of s square is already positive, s is already positive, kp plus 3 should also be positive, right? So Kp plus 3 should be greater than 0. So Kp must be greater than minus 3. So this would give you closed loop stability. Therefore, this is the answer. Now, when we move with the second question, the open loop transfer function is order of what? What is open loop transfer function? It is Gs into Hs. So what is Gs into Hs here? Kp upon S plus 1, S plus 3. Or Kp upon S square plus 4s plus 3. You see, if you try to take out some coefficient, what you would get? S to the power 0 only. That is 1. So n here is equal to 0. Hence it is type 0 system. Okay, I hope this makes sense. We'll move to the next question. The static position error for problem 1 is what? So it is asking you static position error. Okay. So how we are going to find out? So what is static position error? It is Kp and it is limit s tends to 0 Gs into Hs. So limit s tends to 0. What is the Gs into Hs? Kp upon s square plus 4s plus 3. Limit s tends to 0. Put s is equal to 0 here, you'll get Kp by 3. And this is your answer. So Kpe is equal to Kp by 3 is your answer to this question. Okay. Then the steady state tracking error when the stable closed loop system of problem 1 is provided using a unit step reference input. Steady state tracking error. So what is steady state tracking error? It is 1 upon 1 plus Kp. So 1 upon 1 plus, not Kp, it should be K. Then, yeah, Kpe rather. Then it is 1 upon 1 plus. So in our case, it was written to be Kp only. Kp upon 3. So it is 3 upon Kp plus 3. Alright. So what you get the answer? This is your answer. Okay. We'll move to the next question. When the same system is provided a unit ramp reference input. Okay. So what is the formula there? Limit steady state error. Okay, limit s tends to 0. You already had an s here. Here it was 1, and here it was 1 plus GSHS. So the GSHS is Kp upon s square plus 4s plus 3. You cancel out the terms. It would be 1 upon s into 1 plus Kp upon s square plus 4s plus 3, all with limit s tends to 0. So it would, when this s is put to be 0, then what would happen? This whole term would end up being infinity. Okay, so your answer is infinity. Then we can move to question number 6, the static acceleration error. How is static acceleration error is defined? Error constant, sorry. Constant, kv, sorry, ka. Limit s tends to 0, s square gs hs, right? When you write limit s tends to 0, s square kp upon s square plus 4s plus 3, it would give you 0. So this is 0. Okay, so you can verify 0, infinity and everything. So what was the type of the system that you chose? It was type 0 system. So when it was type 0 system, you got infinity here. For steady state error in this case was infinity, and in this case also it is infinity, but what we found out in the question was k, and that was 0. So you can see that you can directly use this anywhere. You need not calculate when you have 0 and infinity kind of situation over there. Okay, next thing, the open loop transfer function of a unity negative feedback closed loop system is this one. For the closed loop system, s is equal to -1. Does it satisfy the magnitude or the angle condition? So how do we define what is magnitude condition or what is angle condition? So if the magnitude is 1 and if the angle is like some 2k plus 1 times plus minus 180 degree, where k can range from 0 to numbers. Basically, it is whole number. So how are we going to answer this question? So if you see the so this is open loop transfer function, right? Open loop transfer function can be written as s plus 1 upon s into s plus 4. Okay, now we want to find out the characteristic equation, because then only we'll be able to say that if this is the case or not. Or there could be another way also, where we try to find out what is the magnitude of this, then also it would work. But let's say if we try to find out the characteristic equation. Okay, so characteristic equation should give me what? That the magnitude is 0. So we'll find the closed loop transfer function first. What would it be? Gs upon 1 plus GSHS. Alright, so it would be s plus 1 upon two s I think I'm missing here. I'm missing this s square plus 5s plus 1, right? Once you get this, Try to put s is equal to -1. What do you get? It would be 1, 1 minus 5 plus 1. So it would be -3, which is not equal to 0. So what we wanted is not here. So it does not satisfy the magnitude condition. Similarly, if you try to find out what is the angle for the system, so you can check from here only that what would you get in tan inverse, and it would definitely not, so angle for OLTF would not be equal to 180 degree multiple 2k plus 1. It would not be the same. Hence, we cannot. So it does not satisfy anything of the following. Okay. So yeah. So we'll start with some root locus questions. And root locus questions are not as a whole root locus question given here. Rather, they are broken into steps. In the next class, we'll have even more not difficult but slightly more engaging questions. Here we can simply solve the questions. So what I would show you, so what is written here? It's open loop transfer function of a negative feedback control system, closed loop system is given by this, where k is some non-integer real valued parameter, then which of the following is true? So how many branches it should have? So what was taught in root locus? We need to locate where are the open loop zeros, where are the poles in the complex plane. Then we want to, so all the branches have to start from open loop pole and terminate at open loop 0. Now if the open loop pole is not equal to open loop 0, then what we do is the curves that are remaining would go to infinity, okay, along some asymptote. So we'll see asymptote later, but they would go to infinity. So let's start with this question, and from here uh, okay, we'll find the other things later. First of all, we will see what are the poles of the system. So what is your OLTF? It is k upon s plus 1 upon s into s square plus 2s plus 2, right? This is your closed loop transfer function. If you try to find out poles and zeros, what would you get? You can see, if you try to derive for this quadratic equation, it would be -1 plus minus j. Okay. If you derive for this, you'll get open loop 0 to be 1. -1, sorry. So once, then you can plot it. Now see. You have a 0 over here for -1. You have poles, 2 poles over here. -1 plus j, -1 minus j. Okay. And one pole at s is equal to 0. So anyway, what we are being asked is, from each pole you should have the branch going to 0 or infinity. So since we have 3 poles, right, and we just have 1 0, so definitely 2 are not going to be coming in, coming to any 0. They'll go to infinity. So what would be the answer? It would definitely have 3 branches, since there are 3 open loop poles. So we need to have branches from there. Then how many will terminate to open loop pole? In our case, it would just be 1, right? So just 1 will terminate. So this is your answer. It would have 3 branches, one of which would terminate at an open loop 0. So this is your answer. Not others are the answers, because all of those zeros would not terminate to any pole. Rather, they would go to, or from all of the poles, it would go not terminate at 0, it would go to infinity. Now the complex conjugate open loop poles are located at, we saw earlier that it is this, sorry, it is this, when you try to solve -1 plus j and -1 minus j. All right. Then in problem 8, in the same problem, The region of the real axis that lies on the root locus is what? So we saw, how do we find what region lies? Before that, I like to plot. This is imaginary, this is real, and then you get a pole to be here, a pole to be -1 plus j, a pole to be here, 1 minus j, and 0 to be here. So how are these defined? What is the region on the real axis that lies on the root locus? So what region lies on the root locus? So there is a rule for this. This is determined by open loop poles and open loop zeros that lie on the real axis. So first of all, we have to consider what is lying on the real axis. We do not have to take what is lying on the imaginary axis or like somewhere in the complex plane. So we are bound to see this part only. Okay, so what parts do we have here now? One is minus infinity to -1 for this part. Another part is -1 to 0. Another part is 0 to infinity. All right. So what happens here is, the rule says choose a test point on the real axis. So in each of these places, you're supposed to choose a test point. If the total number of real open loop poles and zeros are that lie to the right of this test point is odd, then that point lies on the root locus. That means if we choose this region on the axis, x-axis, or the real axis, how many points? So let's say our test point is somewhere here. How many points do you have after this? None. It's 0. It has to be some odd quantity. So definitely this is not the answer. Now you can come at this test point and then try to see how many are lying after this. It is 1. Okay, so this is your answer because the number of poles or zeros lying on the real axis next to the test point is 1. When you come here, you get 2. So this is again not correct. So your correct option is -1 and 0. Okay. Now what is the number of asymptotes? So how would you tell what is the number of asymptotes? First, let me copy this question also. So what happened? Did not get copied. Okay. So I'll write it down. Ks was +1. Right? What is the number of asymptotes? Number of asymptotes is n minus m. Now what is n here? Because the number of asymptotes would be of such kind only along which we are going to go to infinity. So it is basically going to be that what number of poles are not terminating at what number of zeros. So agar pole hai, if it is 3, and for 0 if it is 1, definitely one pole is going to terminate at open loop 0, but the other two open loop poles are going to infinity. So if they are going to infinity, they must have some asymptote. So that is why we are having this asymptote thing here. So what is your n here? Is it 3? What is your m here? It is 1 because 3 from here and 1 from here. Then what is the number of asymptotes? It's n minus m, which is equal to 2. So 2 is your answer. Okay, these are the number of asymptotes. Then, so this is basically the order in which the questions are being discussed is the way to solve a root locus problem. Now, the angles in degrees made by the asymptotes with the positive real axis are what? So you see what is this formula given here for angle with the positive real axis. It is plus minus 180 degree 2k plus 1 upon n minus m. What was n minus m? 2, where k can be 0, 1, 2 and so on. So since we just have two asymptotes, putting the value of k to be 0 would give us the answer. So it would be plus minus 180 degree by 2. It would be plus minus 90 degree. Okay. And what is plus minus 90 degree? What is plus minus 90 degree? It is basically 90 degree and 270 degree, right? Because 90 degree is here, minus 90 is here. So if you go in this direction, it would be 270 degree. So this is your answer. Okay. Once you have got what are the poles, what are the zeros, which area on the real axis would lie, would be the region for root locus, then you're supposed to find out what are the asymptotes, what are the number of asymptotes, where do the asymptotes intersect. Then your next point is if they are intersect, what angles do they make and where do they intersect. So the next question that we're going to have is basically based on the intersection of the asymptotes. So you can see the point of intersection of asymptote is what? Okay. So so how do we say that? Point of intersection is given by negative of sum of open loop poles minus sum of open loop 0 upon n minus m. So basically this. Try to remember this. Sum of open loop poles minus sum of open loop zeros upon n minus m. Okay. Okay. So how we are going to find this? So it would be negative of or what is the sum of open loop poles? 0. One of the poles was 0 in our case. One was minus 1 plus j. One was minus 1 minus j minus of minus 1 because 0 is minus 1 here. Okay. When you did this and upon n minus m, so it is going to be 2. So it is minus 1, jj cancels out, minus 1 plus 1 upon 2. So it is minus 1 upon 2. So minus 0.5 is the answer. So this is basically the point of intersection of the asymptotes. Okay. Now the next question is, which one of the following is true about problem 8? So what was problem 8? I'll write it once again. We are actually doing the same question. So OLTF was k into s plus 1 upon s cube plus 2s square plus 2. Right? Now, here we want to find what is break-in and breakaway point. So when we try to determine the break-in and breakaway point, so it will exist on the root locus between two consecutive open poles or zeros on the real axis with no real open loop zeros between them. Okay. So how it happens? So is there any consecutive open loop pole or zero present over here for the first case? There should not be anything between them. There should be at least two closed loop poles together or two closed loop zeros together without having any pole or zero in between. Do we have such situation here? Because one pole is here, one pole is here, one pole is here, and a zero is here. So there are not even two poles on the real axis. If there are not two poles on the real axis, there is no going to be a break away or break in point. All right. If there were, then we would have applied this condition. But since it is not there, we need not do that. Okay, so from here only. So how this comes actually, this will discuss later also. But see, 1 plus k into as upon bs. Now, if you write it as k is equal to, what would you get? Minus bs upon as. Then you differentiate dk upon ds, and you'll get this term. So you can directly differentiate also when you have k in terms of s. Then you'll be able to differentiate to find out where are the break-in and breakaway points. All right. Then we'll move to the last question. In this case, in problem 8, the closed loop system would be stable for what? So if we want to find out the closed loop system would be stable for what, then what we can do here is we can write, so your OLTF was what? Just let me see once more. K into s plus 1 upon s cube plus 2s square plus 2s, right? So what was your closed loop transfer function? It is k into s plus 1 upon s cube plus 2s square plus 2s upon 1 plus k s plus 1 s cube plus 2s square plus 2s. So it would be ks plus 1 upon s cube plus 2s square plus 2s plus, sorry, k plus 2 s plus k, right? Now your characteristic equation is what? S cube plus 2s square plus k plus 2s plus k, right? Now what do we want? We want that how do we ensure the stability of the system. So if we want to know if the system is stable or not, so what we are going to do? So we are going to see using Routh-Hurwitz stability criteria. So first of all, Hurwitz polynomial, we should have the coefficients of all the s already present here, and that is true in this case. Secondly, what we want is that all the coefficients should be of the same sign. So for the first term, the coefficient is 1, which is positive. For the second term, the coefficient is 2, which is even positive. For the third term, coefficient is positive or not, that can be ensured by saying k plus 2 should be greater than 0. So k should be greater than minus 2. In this case, it can be written as k should be greater than 0. Then we can go for Routh's array. So you can write s cube, s square, s to the power 1, s to the power 0. 1, 2, k plus 2, k. Then you can try to multiply. So it would be 2k plus 2 minus k upon 2. So what is this equal to? 2k plus 4 minus k upon 2. Would give you 2, would give you k plus 4 upon 2. So from here you get k should be greater than minus 4. Now we'll go for the next step where you'll multiply k plus 4 upon 2 into k, right? Matlab this term here into this term, and you'll divide by the same term. So it would be k plus 4 by 2. This cancels out and you get k. So k should be greater than 0. So k should be greater than minus 2. K should be greater than 0. K should be greater than 0. Here k should be greater than minus 4. Here k should be greater than 0. So if you want stability, we would want k to be greater than 0. Okay. Do you have the option here? Yes, we have the option here. So k should be greater than 0. So since we have done this question, so what did we find here? There were two closed loop poles, sorry, open loop poles, which were like some lying as conjugate pairs in the S plane. there was one closed loop pole at s is equal to open loop pole at s is equal to 0, and then there was one open loop 0 at s is equal to -1. So if we were supposed to do this in MATLAB, what we could do? So I'll show you that. Let me change the screen for recording first. So I'll switch to MATLAB as the screen, and I'll have to I'll present it, just a minute. Okay, so you can see this MATLAB screen. So this is the code for the same example that you have. So I have defined numerator and denominator here. Now how the numerator and denominator is defined? So what was your numerator? It was k into s plus 1, right? So s plus 1 means s ka coefficient is this one. 1 is already 1. So you define in order of the polynomial from highest power of s to lowest power of s. So it is 1 1. For the denominator, we had s cube plus 2s square plus 2s plus 0. There was nothing for s to the power 0. So we write it in that way. So for corresponding to this, coefficient of s cube is 1. Coefficient of s square is 2, coefficient of s is 2, and coefficient of s to the power 0 is 0. Hence, the transfer function is defined. So, how do we say that? So, we write system. Some system is equal to transfer function numerator upon denominator. All right. So, we can use this command window also. Command window is generally used to access any kind of variable. If you want to do some operation, or you want to know what is the value, it is a very good tool for debugging. Moreover, you can have some programs over here also, but we generally prefer to do it in the editor, and then we want to see what is happening in the command window. So in command window, when you try to this statement is terminated by a semicolon. In that means that we want that we should not have this value of sys printed over here, but uh, uh, if you remove this semicolon colon, you will be able to see this in the command window. So what I did, I wrote in the command window this variable sys just to look at what is the transfer function. And you see this was the transfer function given to you in the question, and it is printed over here. So you write it numerator and denominator, and then you write TF. And I want to know what is the root locus for this. So you can see here, this figure is written because I want to generate a figure. Then there is a command r locus sys. So for the system you're trying to generate the root locus, then you give the title to be root locus for the transfer function. This is what, and you keep the grid to be on, and then you want to observe what is the root locus over here. So I'll show you. When I run this MATLAB, what happens? I'll change the window again because it is not capturing. Does not show me this. How to show this? Yeah, it gives me an option for figure 1. So you can see that this is the root locus. So there was a pole as we saw here minus 1 plus j. There was a pole here minus 1 minus j. There was a pole at s is equal to 0, and then there was this 0 over here at s is equal to minus 1. Okay, now you can see that the poles move from here. One of the poles that is at s is equal to 0 terminates at the pole, terminates at the 0, s is equal to minus 1, right? Now the two other poles have to terminate somewhere. So since they do not find any other open loop 0 to be present here, they go to infinity. So both of them are going to infinity, but since they're going to infinity, they have to go along some asymptote. So the asymptote value here is at minus 0.5. The value that we had derived, that the asymptotes are at minus 0.5. So along that line only it is going. And you see there are no consecutive poles, no consecutive 0. So since we do not have them, so there are no break in and break away points, and it is even not crossing the imaginary axis. So if in any case it does cross the imaginary axis, then we'll have to find out that point also. And since it does not cross here, so that was not considered. But you can just put j omega in the equation and try to find out at what value of omega it is going to cross, and so on. So that is one of the ways to do. So yeah, so when you are at the pole, you are at your k value is at 0. So when you're here, you are at k is equal to 0. When you're here at pole, k is equal to 0. When you're here at pole, k is equal to 0. And as you move in this way towards any side, okay, if you move, then you move from k to 0 is equal to 0 to k is equal to infinity. Okay, anytime you approach any 0 or move to infinity. So this is the way we can you can always solve the root locus question and check in MATLAB that if your answer is correct. So this gives you a good like practice for the root locus questions also. So you can always verify using this. Okay, so this was a very simple program for the root locus. In the next class, we'll have some more nice questions on root locus, and we'll be seeing them. So yeah, for today, we are done with solving the problems. See you on next Monday. Thank you.